Prove that 11 divided by 37 is 0.297 bar. And it's not enough to just simply plug into a calculator and see that the pattern looks like it works. So if I just simply take 11 divided by 37, lo and behold, it does look like the pattern does work. 0.297, 297, 297, and 3 because 9 looks like it rounds up to, or 0.29 would round up to 3 in the last place here. So we have certainly a very compelling reason to think that it works based on the calculator, but that's not a proof because the calculator only displays the first 10 digits, and there's no guarantee that the pattern would not break after 10 or 12 digits. Now, it is correct, but we can't prove it by just simply plugging into a calculator. Alright, so how do we prove this? I'm going to talk about this several different ways. The easiest ways are going to go from the right-hand side to the left-hand side. Going from the right-hand side to the left-hand side. In other words, starting with the decimal representation and then converting to a fraction. One way of doing this is to let x be equal to 0.297 bar. So 297, 297, and so on. If I multiply this by 1,000, then this would be 297.297,297. And then if I subtract these, I would get that 999x is equal to 297. And so that x is equal to 297 divided by 999. And it turns out that 27 is a common factor to both numerator and denominator. And so dividing top and bottom by 27, we get 11 divided by 37. So that's one way of establishing this, going from the right-hand side to the left-hand side. A second way is just simply you can write down that 0.297 bar is equal to 297 over 999. That's a theorem that we proved in class, and the proof of the theorem basically goes according to the logic that you see here on the screen right now. So 0.297 bar automatically is 297 divided by 10 to the third minus 1, or 999. So let me just write that down, that 0.297 bar from a theorem that we have in class is equal to 297 divided by 10 to the third, because the repeating block has length 3, minus 1. So, and from there we can cancel out and get 11 over 37 again. So that is another thing we can do. A third thing that we can do would be that 0.297 bar is equal to 0.297,297,297, and we get this directly as opposed to indirectly. And the way that we get this directly is by using a geometric series. So this is 297 divided by 1,000. That's the first 3 digits. For the next 3 digits, it's 297 divided by 1,000,000. That would be 0.000297, and that would produce the next 3 digits. The next 3 digits after that would be 297 divided by 10 to the 9th. So just to write the numbers on top, so this part here is 0.297. This part is 0.000297. This part is 0.12345 zeros 297. And if we continue along this way and then add these decimals up, we would get the infinite representation here. This is an infinite geometric series. The first term, of course, is 297 divided by 1,000. The common ratio is 1 minus 1 over 1,000, because you multiply by 1 over 1,000 to go from one term to the next. And then this simplifies as 297 divided by 999. And so that is the answer. So that's the easy way about going this, going from the right side to the left side. The harder way, so harder, is going from the left-hand side to the right-hand side. In other words, the fraction is given, and you don't have a calculator, and you're trying to figure out how to prove that 11 over 37 is equal to 0.297 bar, starting directly from 11 over 37 and ending with 0.297 bar. Okay, so how do we do this? Well, the brute force method would go as follows. 11 divided by 37, and we simply use the division algorithm. So 0.0, well, let's see, we know what the answer is going to be. 2, carry the force, so 74. Subtracting, we get 6, 3. Then bring the next 0 down. We know it's going to be 9 here. 9 times 7 is 63. Carry the 6. 9 times 3 is 27, plus 3 is 33. That brings down 27. Bring down the next 0. And then, we know the next answer digit is going to be 7. So 7 times 7 is 9. Carry the 4. 21 times 7 times 3 is 21, plus 4 is 25. And when we subtract, we get 11. And that's our guarantee that the pattern is going to repeat. I started with 11, and I ended up with 297. So because I have 11 again down here, I know that I'll have 297s in perpetuity after this. So because the 11 here, I have the same remainder basically, 11, 11, I know that the next digits will be 297, then 297, then 297, and so on. So that implies that 11 over 37 is equal to 0.297 bar. Stated another way, if I look at what I have written down here so far, if I move the decimal spot over 3 places, I know that 11,000 is equal to 200. Let me change colors here just to make this a little easier to see. I know that 11,000 is equal to 297 times 37 plus 11. That's the work that I've done so far in computing the fraction, and therefore I know that 11 times 1,000 minus 1 is equal to 297 times 37. Bringing the 11 over to the other side. And so this means that 11 divided by 37 is equal to 297 divided by 999. And we have a theorem in class that says that if I have a fraction of that form, I know already what the representation is going to be. I just simply take the numerator and repeat it infinitely many times. So that is a way of getting another equivalent way of proving that the fraction 11 over 37 is equal to 0.297 bar using, again, the division algorithm, knowing that 11,000 is equal to 297 times 37 plus 11, and then rearranging terms to be able to write out the fraction and change that fraction into a decimal. A third way of doing it, which is slightly less elegant but certainly is logically correct, is as follows. Well, 37, let's just start experimenting. 99 divided by 37 doesn't work. 999 divided by 37 does work, 27. And so that would allow me to write 11 over 37 is equal to 11 times 27 over 37 times 27, which then converts to 297 over 999, which is therefore equal to 0.297 bar. So there's about 6 different ways of being able to prove that the fraction is equal to the decimal. They're all logically equivalent, of course, just taking the same idea and twisting it in different ways.